In this episode, we take a big idea that sounds intimidating at first and make it feel like a practical way to revise what you believe when new information shows up. Bayes' theorem is often introduced with heavy math, but at its heart it is a rule for updating your expectations when you learn something new. That matters in data work because you rarely start with perfect knowledge, and you are constantly adjusting your understanding as more data arrives. If you have ever changed your mind after seeing additional details, you have already done the human version of this idea. The goal here is to make the formal version feel natural, so you can read exam questions with confidence and avoid the common traps that come from confusing what is being conditioned on and what is being predicted. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Before you can use Bayes' theorem comfortably, you need a clear mental picture of conditional probability because Bayes is built out of that concept. Conditional probability is simply the probability of an event given that another event has happened. The word given is doing the most important work because it tells you that you are no longer living in the full universe of possibilities. You have narrowed your view to only the situations where the given condition is true, and then you ask how often the event of interest occurs inside that smaller universe. Beginners often treat conditional probability like a magic operation that changes the world, but it is really just careful bookkeeping about what information you are assuming. When you keep that bookkeeping mindset, the rest becomes less mysterious because you stop mixing up the direction of the condition. It is also important to separate two ideas that sound similar but are not the same: the probability of evidence given a hypothesis and the probability of a hypothesis given evidence. These phrases look like mirror images, and many test mistakes come from treating them as interchangeable. For example, the probability that a test produces a positive result if a condition is present is not the same as the probability that the condition is present if the test is positive. The first is about how the test behaves under a known reality, while the second is about what reality is likely given an observed result. Bayes' theorem is the bridge between those two directions, and it is valuable precisely because humans instinctively confuse them. If you train yourself to slow down and say, "Given what? Then what?" you immediately reduce that confusion. This is one of those topics where careful language is not optional, because language is the map. Now let's talk about what Bayes' theorem is doing conceptually, without diving into symbols right away. You start with an initial belief about how likely something is, and that initial belief is often called a prior probability. Then you observe evidence, like a measurement, a label, or an outcome, and you ask how that evidence should change your belief. The updated belief is often called a posterior probability because it comes after you see the evidence. The piece that connects the two is how compatible the evidence is with the hypothesis, which is often called a likelihood. Bayes' theorem tells you how to combine the prior with the likelihood while also accounting for how common the evidence is overall. That last part matters because evidence that is common for many reasons should not dramatically shift your belief in one specific cause. A helpful way to make this feel real is to imagine that you are sorting explanations, not just computing numbers. Suppose you have two possible explanations for a behavior in data, like whether a pattern is caused by genuine user preference or by a measurement artifact. Before seeing any specific evidence, you might believe one explanation is more common based on general experience, and that is your prior. Then you see a particular signal in the data, and you ask, if each explanation were true, how likely would I be to see this signal? That is the likelihood comparison, and it tells you whether the signal supports one explanation more than the other. But you also must ask how often that signal appears in general, because a signal that appears everywhere is not strong evidence of anything. Bayes' theorem is essentially the rule that keeps these pieces from being mixed together in an inconsistent way. Many exam questions about Bayes are really testing whether you respect base rates, which are just the underlying frequencies of things before you observe evidence. Beginners often focus on the evidence and ignore the base rate, especially when the evidence sounds impressive, like a test described as highly accurate. This is where people make the classic error of assuming that a positive result almost certainly means the condition is present, even if the condition is rare. If something is rare, most people do not have it, and that fact remains true even when tests are good. Bayes' theorem forces you to combine the rarity of the condition with the test behavior, which can produce results that surprise beginners. This is not about being pessimistic. It is about being mathematically honest about how much a single piece of evidence can move your belief. The exam often rewards the answer that correctly accounts for rarity rather than the answer that is dazzled by a high accuracy number. One of the most beginner-friendly ways to think about Bayes is in terms of counts in a big imaginary population, because counts are easier to reason about than pure fractions. Imagine a large group of people or items, where only a small portion truly have a condition and the rest do not. Now imagine a test that sometimes correctly detects the condition and sometimes produces false alarms. If you mark who tests positive, you will have a pile of true positives and a pile of false positives. The probability you actually care about, the probability of the condition given a positive test, is essentially asking what fraction of that positive pile is truly positive. When the condition is rare, the false positive pile can be surprisingly large compared to the true positive pile, even with a strong test. Bayes' theorem is the formal version of that pile comparison, and the piles help you keep your intuition aligned with the math. Another core skill is recognizing what exactly is being updated when new evidence arrives. Because Bayes does not update the world, it updates your belief about the world. That sounds philosophical, but it is actually a practical distinction on exams. If you see a new measurement, Bayes is not changing the underlying system. It is changing your probability estimate about which explanation is most plausible given what you observed. In machine learning settings, this shows up when you treat predictions as probabilities, like the chance that an item belongs to a class, and then you revise those probabilities when you get new signals. It also shows up in reasoning about models that combine different sources of evidence, where each source shifts your confidence a bit rather than deciding everything alone. Beginners sometimes assume that probabilities must become either 0 or 1 once evidence appears, but real evidence is usually imperfect, so updates are usually partial. Bayes is the rule for partial updates that remain consistent over time. You also need to be careful about what it means to condition on evidence, because conditioning is not the same as causation. If you compute the probability of an event given a feature, you are not claiming that the feature caused the event. You are simply describing how often the event occurs when the feature is present. This matters because data often contains correlations that are not causal, and Bayes can be used in situations where causation is unknown. An exam question might describe a scenario where a variable is associated with an outcome, and then ask you to update probabilities based on that association. The right move is to treat the association as evidence, not as proof of cause. If you interpret conditioning as causation, you can be pushed into wrong answers that make overly strong claims. Bayes is comfortable with uncertainty, and your language should be too. There is also a common confusion between updating a single hypothesis and comparing multiple hypotheses, and Bayes can handle both, but the mindset is slightly different. When you update a single hypothesis, you are asking how likely it is after seeing evidence. When you compare multiple hypotheses, you are asking which of them becomes more likely relative to the others after seeing the same evidence. In practice, many decisions are comparative, like deciding which model explanation fits better or which class label is more plausible. The comparison framing is helpful because it focuses you on relative support rather than absolute certainty. Evidence can increase the probability of one hypothesis while decreasing another because total probability has to be distributed across possibilities. This is why Bayes is often described as redistributing belief mass in response to evidence. If you remember that it is redistribution, you avoid the mistake of thinking that every hypothesis can become more likely at the same time after the same evidence. In data AI contexts, Bayes' theorem often appears under the hood in systems that combine signals. But for the exam, you usually need to reason at a high level, not implement anything. For example, you might be asked why a model that sees a rare class should adjust its predicted probabilities, or why a threshold decision should consider prior odds. You might also be asked to interpret a statement like the model outputs a probability, and that probability depends on both the evidence and the base rate. Bayes gives you the vocabulary to explain why those statements are true. It also helps you see why changing the population can change your results, because a prior that reflects one environment might not reflect another. If the prevalence of an event changes, the posterior probability for the same evidence can change as well, and that is not a contradiction. It is a reminder that probabilities are conditional on context, which is exactly what the theorem formalizes. A powerful exam-ready habit is to label the parts of a Bayes problem in plain language before you touch any numbers. Ask yourself, what is the hypothesis I care about? What is the evidence I observed? And which direction does the question want? If the question says the probability of a positive test given the condition, that is a test behavior statement, not the final belief statement. If the question says the probability of the condition given a positive test, that is the belief update statement. Once you identify the direction, you can decide whether Bayes is needed or whether the question is simply about reading the given probabilities correctly. Many tricky questions are tricky only because they hide the direction inside a long sentence. When you translate the sentence into a short given and asked pair, the confusion fades and the correct approach becomes obvious. Another misconception to clear up is the idea that Bayes is only for medical testing or only for people doing advanced statistics. In reality, it is a general rule for reasoning with uncertainty that shows up anywhere you have incomplete information and new evidence. In security and data scenarios, it can appear in thinking about whether an alert indicates a real issue, whether a user behavior is anomalous, or whether a model's prediction should be trusted given the costs of errors. You do not need to calculate complex posteriors to use the concept. Often you just need to reason about whether evidence is strong, whether the base rate is low, and how those factors should influence your confidence. The exam often tests that kind of reasoning because it aligns with real decision-making. If you can explain in simple terms why a rare event changes interpretation, you are using Bayes thinking correctly. That is the level of confidence you want. To bring everything together, Bayes' theorem is your reliable method for updating beliefs when new information arrives, and the key is to keep your conditions straight. You learned that conditional probability is about narrowing the universe to situations where the given information holds, and then measuring frequency inside that narrowed set. You learn that the probability of evidence given a hypothesis is different from the probability of a hypothesis given evidence, and that Bayes is the bridge between those directions. You learned why base rates matter and how ignoring them leads to confident but wrong conclusions, especially when events are rare. You also learned practical ways to stay grounded, like reasoning with counts, labeling hypothesis and evidence in plain language, and remembering that Bayes updates beliefs rather than rewriting reality. With these habits, you can handle Bayes questions as structured reasoning problems instead of as scary formula problems, and that confidence will carry forward into later topics like hypothesis testing, classification thresholds, and interpreting model outputs.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.